Good morning, everyone. And this is EMI lecture number 3. And in the previous lecture, we have seen different cases of how we can induce current by changing magnetic flux. We had seen that the phi, magnetic flux phi is B A cos theta. We can change this magnetic flux by changing either B or A or theta. Any of these things, if we change, we will be able to change the magnetic flux and current will be, EMF will be induced. If there is a closed loop, we'll have current. EMF and current is inversely proportional to time. The faster you do it, the more is the EMF or current. But charge flowing through the circuit does not depend on time. It only depends on the change in flux, and it depends on the type of the material of the body in which this flux is induced, because it depends on the resistance of the circuit. Do we remember this? Yes or no? Okay. Then now, as I told you, in today's class, we are going to see the different ways in which this flux can be changed. And as I said, there are three things here. There are three things which are involved here for flux. Flux is BA cos theta. You can change the flux by changing any of these, or by changing two of these, or by changing all three. Any question which has all the three changing or all two changing will not come. We'll have only one of these changing. So in case number one, which you may call as static EMI, nothing moves. Area and angle theta remain constant. Only magnetic field changes, and the rate of change of magnetic field is dB by dt. Because of this change in the magnetic field with time, we have seen that electric field E is produced. That electric field is known as induced electric field. We have seen about that induced electric field in the last lecture. You can always go through the last lecture. The static EMI, no, nothing will move. Only magnetic field will change. Flux would be induced and a current will come. This can happen in two ways. Can happen by self-induction in the coil, or it can help by mutual induction. We will be taking those things today. Don't worry. The second case is when P and theta, magnetic field and theta, remain constant, but your area changes with time. This was the case that we did when the wire was moving and area was changing. We had seen some question in Lenz's law how to find out the direction of induced EMF or induced current. This type of EMI, since things are moving, you can call this as dynamic EMI. A straight wire was moving. We have seen that cases in Lenz's law. In the third case, magnetic field B and area are not changing. Only angle is changing with time. Now, this is the way in most cases EMF is generated, and we will be dealing with this more in the next chapter, which is alternating current. The alternating generator, the way electricity is generated in power plants, it is by this method of changing angle with time. You have a coil placed inside a magnetic field, and that coil starts to rotate. When that coil starts to rotate, theta changes with time. B and A remain constant. This is known as periodic EMI. Your EMF or current will keep on changing periodically. That type of EMF or that type of current is known as AC. Have you heard the term AC? Yes or no, bacha?
Yes, sir.
That is your periodic EMI. So these are the three different cases or three different branches in which you can segregate the EMI. I'll give you a minute to note it down and I'll be back. Now let us deal with those cases one by one. The first thing is the static EMI. Nothing is going to move. What are we going to do? We'll have a coil. Coil is nothing but a wire turned like this. This coil has an area. I am going to change the current in the coil. Whenever current flows through a coil, it creates magnetic field. If I change the current, magnetic field will change, flux will change, and I would have an EMF generated. So basically what is happening, a EMF would be generated in the coil because of changing current in the coil. Your current is changing in the coil, and because of that, EMF is induced in the coil. This type of EMF is known as self-induced EMF, and this concept is known as self-induction. As you can see, when current through the coil changes with time, then the magnetic flux linked with the coil also changes time. Due to this, an EMF and a current is induced in the coil. According to Lenz's law, this induced current opposes the change in flux. Flux is changing because of change in current. This induced EMF will oppose the change in current. That means if the current is decreasing, it will try to increase. If the current is increasing, it will try to decrease. This phenomena is known as self-induction, and this property is known as self-inductance. Do we understand this?
Yes, sir.
The self-induced EMF or the self-induced current will oppose the cause. The cause is changing current. So if the current is increasing, it will try to decrease. If the current is decreasing, it will try to increase. I'll give you a minute to note this down in your notebook. This phenomena, this principle, this process is known as self-induction, and the property is known as self-inductance. A minute to write it down. Let's move ahead and see how we can measure this property of the coil. We can measure this property of the coil by something known as L, which is the coefficient of self-inductance or simply self-inductance of the coil. Here, bacha, as you can see, there is a coil. Do you see this? This coil is turned like this. So this coil has an area. If there is current in the coil, there would be a magnetic field in the coil. Because there is an area of the coil, it will have a flux in the coil. If current is constant, there will be no induced EMF. But you can say that the total flux of the coil will be directly proportional to the current. Do we understand this? Because flux comes from field and field is coming from current. So total flux will be equal to Li, or I can say this L is equal to N phi by I. Phi is N into B into A into cos theta, or it is total flux divided by I. This L is known as the self-inductance of the coil. From here, we can also find its unit. The SI unit of flux is Weber. The SI unit of current is ampere. So I can say the SI unit of inductance will be Weber per ampere. Do we understand this, bacha? I'll give you a minute to note it down. This is one way of measuring the self-inductance of the coil. Find out the total flux divided by I. That is your self-inductance. A minute to win it. Now what will happen if the current starts to change, beta? It's very easy to understand. If the current changes with time, di by dt, that will make the magnetic field to change with time. That will make flux to change with time. And whenever flux changes with time, you will have an induced EMF. N phi is equal to Li. We have already seen that. Remember, L is a constant. It does not depend on current, does not depend on flux. L only depends on the medium surrounding the coil. Please note it down. And it depends on the geometry or area of the coil. Does not depend on current, it does not depend on flux, it depends on medium and the geometry of the coil. Now, when flux changes with time, EMF will be induced in the coil, and you can write the induced EMF as minus L di by dt, minus sign coming from Lenz's law. It indicates that the induced current or induced EMF will oppose this rate of change of current. From here, you can find out the SI unit, one more SI unit of L, that is equal to volt divided by ampere per second. Do we understand this, bacha?
Yes, sir.
I'll give you time to note this down. Two ways of writing the formula for self-inductance. Let's move ahead and see some golden points. As you can see here, if you have a thin wire which is not turned like this, its inductance would be zero. It will have no inductance because the area is very less or zero, but it will have some resistance. All wire have resistance. This is how you denote R. What does resistance do? It opposes the flow of current. If you mold this resistance in this form, it will have resistance as well as it will have inductance. So it will be a combination of L and R. It will be a LR combination. L standing for inductance and R standing for resistance. Remember, the role of L is to oppose the change in the current. If the current becomes constant, the current is constant, L will not do anything, but resistance will always be there. Resistance is possible without inductance. So you can have a wire which has zero inductance, but it will have resistance. But you cannot have a wire which has zero resistance and it has inductance, because inductance comes from the wire and wire always has resistance. But in the question that you are going to do, we are going to take wire as pure inductor. It is not possible, but theoretically it is not possible, but practically some questions we might take it as a pure inductor. Remember, a pure inductor is not possible. A wire must have resistance. Do we understand this, bacha? Role of resistance is to oppose the flow of current. Role of inductance is to oppose the change in current. If the current is not changing, L does not do anything. I will give you a minute to note it down. So now what we see is what will happen if current increases. You can see if current increases with time, rate of change of current would be positive, and EMF which is induced will be negative. It will be opposing your actual EMF, and hence your net EMF will be total EMF of the source minus the induced EMF. But if your current is decreasing with time, Your rate of change of current would be negative. In that case, your EMF would be positive and it would be in the same direction as the original EMF. Do we understand this, bacha?
Yes, sir.
Please note it down. It gives you time. So basically, this induced EMF is going to oppose the cause of change in flux. Your flux is changing. By changing in current, if the current reduces, it will try to increase the current. If the current increases, it will try to reduce a minute to minute. Now you will come across cases where you will see a question on what will happen when the key is open and what will happen when the key is closed. When they are talking about the key, what they are asking is, or what they are talking about is when you switch on or switch off the circuit. So there will be an inductor in the circuit, there will be a switch or a key. As you can see, I have drawn it. What will happen when the switch or the key is opened or the switch off or the key is closed? When you close the key, current will try to increase. Rate of change of current is positive. Induced EMF would be negative. When the key is open or the EMF is cut out, current will decrease. The inductor will try to increase the current and the induced EMF will be positive. At the time of sudden opening of current due to high inductance of circuit, a large momentary EMF is induced and sparking occurs. So you may have seen spark. That sparking occurs because of this inductance. To avoid sparking, a capacitor is connected parallel to the key. Remember that. How do you avoid sparking? To connect a capacitor, it will store that energy. Self-inductance always opposes the change in current, so it is also known as inertia of electric circuit. It is just like inertia. What do you mean by inertia? If a body is at rest, it will remain at rest. If a body is moving, it will try to continue its motion. It will always try to oppose the state of motion. That property is known as inertia. You can call inductor as the inertia of the circuit because if you try to change the current in the circuit, inductor will oppose it. Do we understand this? Yes or no? I'll give you a minute to note it down. You can look at this table and try to understand the equivalence between the terms that we had seen in mechanics to the terms that are there in electricity. If you call inertia as mass, in mechanics, you can call electrical inertia as L. Inertia opposes change in velocity. Inductance opposes change in current. The other thing that you can say, inertia opposes is momentum. Here you have change in flux or magnetic flux. Body has kinetic energy. When you change velocity, kinetic energy changes. When you change current, magnetic energy changes. The retarding force or the force with which it is trying to oppose it is minus MA or minus M dV by dt. Here it is minus L di by dt. Do we understand this, bacha?
Yes, sir.
I'll give you a minute to note this down. I've seen question coming on this, so please remember it. Very important topic. Then one more thing you must note down. If you have two coils and they are laid in opposite manner, one in this way, the other one in the other way, carrying current in the opposite sense, then you will have the inductance almost equal to zero because current, the flux in one coil and the flux in the second coil will cancel out each other. Do we understand this? Just note it down. Opposing currents. Let us see some questions on this, and this is from your practice exercise. on page number 123. Question number 1, and this is the question. These are the type of questions you can expect in the exam. The value of self-inductance of the coil is 5 Henry. Remember, the SI unit is Henry. 1 Henry is 1 Weber per ampere. The value of current changes from 1 ampere to 2 ampere in 5 seconds. What is the value of the induced EMF? I'll give you time to solve it. You have 2 minutes to do it. I've highlighted the important points. Remember the formula. Put these things in the formula and you will get the induced EMF. Okay, so how are we supposed to do it? Just apply the formula. Induced EMF is equal to minus L into change in current. Let me call it as delta I divided by change in time. Let me call it as delta T. Negative sign only indicating that it is opposite to the change in current. Just put the formula. L is given as 5 multiplied by how much the current is changed. Final value is 2. Initial value is 1. The current changes from 1 to 2. So change in current is 5. In how much time this current has changed? This current has changed in 5 seconds. That is the value, my dear friend. You will get 1 volt. Do we understand this, bacha? Just 2 formulas we have read, beta. What are the 2 formulas that we have read? You must be knowing those formulas, beta. Yes or no? No or yes? Only 2 formulas we have done. The first formula is N phi, the total flux, is equal to Li. So some question can be done by this formula. The other formula is E is minus L delta I by delta T. The other questions can be done with this formula. Do we understand this? Yes or no? No or yes? I hope. I hope. I hope. You can do the next question. Yes or no? No or yes? Well, I love this confidence. And here comes the next question. Read the question carefully and then give me the answer. I'll wait for 2 minutes. You have a coil of self-inductance 2 Henry. It carries a current of 2 amperes. The direction of current is reversed, bacha, in 1 second. What is the induced EMF? And I shall wait for your answers. Well done. If you could do this question again, how are we going to do this, beta? We are going to apply the formula. E is minus L into change in current delta I by the time delta T. So EMF will be equal to, let me forget the negative sign because it is only going to tell us the direction. The value of L is given as 2 multiplied by how much the current has changed. Initially the current was 2 ampere. So let me call it as 2. Then the direction of current is reversed. So if it's 2 was like this, now the direction becomes like this. So how much is the change in current? If I call this as plus 2, this will become minus 2. So 2 minus minus 2, the change in current will be 4 amperes. Do we understand this, bacha? Divided by the time, so it is 2 multiplied by 4 and the answer becomes 8 volt. So my dear friends, 8 volt is the answer. I hope you understand this. Yes or no? No or yes? Do we understand this, beta? Well, let me give you a question from previous years. And this is the question that I'm talking about. I hope you can give me the answer very fast. And the question goes like this. The current is a coil of 0.1 millihenry, M standing for millibeta. Coil increases by 250 milliamps 0.1 seconds. Can you tell me what is the induced EMF here? Tell me what is the induced EMF here. I'll wait for you for 1 second. Then well done. The inductance is L is given as 0.4 millihenry. Everything is in millihenry. They will get cancelled. Millihenry is 10 raised to power minus 3 Henry. Current increases, so change in current is 250 millihenry. The induced EMF 0.1 seconds, time is 0.1 second. Everything is given. You can apply the formula E is minus L di by dt and you will get the answer. Yes or no? Do you understand this better?
Yes, sir.
Do you want me to solve it or you know how to do it? Yes or no? No, yes. Shall I move to the next question, bacha?
Yes, sir.
Okay, let me see. Where is the question? It will be here. Lots of questions here. Let me see which one can we do now. Last one. And I hope if you can do this one, you have understood the concept behind this. So this is the one. Question number 43 from your sheet. The value of self-inductance of a coil is 5 Henry. Current in the coil changes from 1 ampere to 2 ampere in 0.5 seconds. What is the magnitude of the induced EMF? I hope you can do this. Yes or no? No, yes. Give you a minute to do it. So how we got to do this? The self-inductance is given as 5 Henry. Current changes from 1 ampere to 2 ampere. So you know the change in current. You know the time. Change in current is 1 ampere divided by the time. 1 divided by 0.5 is 2. 2 multiplied by 5. And the answer would be 10 volts. Do we understand this? Yes or no? No or yes?
Yes, sir.
So the questions on this type is very simple. Now we move on to the next category of question. The theory behind it. And those questions are based on the value of self-inductance. How can you change the value of self-inductance? What is the value of self-inductance for different coil? There has been some misprint over here, so forget about that. You have a plain circular coil, as you can see. You can see this plain circular coil. The radius of the coil is R. The number of turns in the coil is N. And if you find the self-inductance of the coil, how do you do it? That is not what you need to understand. You must remember this formula for self-inductance of the coil, mu naught into N square into pi R by 2. That means it depends on mu, it depends on the medium, it depends on N square. That means it is directly proportional to the number of turns per square. If you make the number of turns twice, inductance will become 4 times. It is directly proportional to the radius. If you make the radius more, the inductance will change. Please remember these formulae and remember these points. All the questions are based on these two things. Self-inductance of a plain circular coil. That was the self-inductance of a plain coil. What happens with a solenoid? That is the next thing that you have to understand. For a solenoid, the self-inductance is given by a similar formula, mu naught N square A, where A is the cross-sectional area of the solenoid divided by L, where L is the length of the solenoid. Yes, you can write it in terms of small n. where small n is the number of turns per unit length. So this is also one formula that comes. Capital N is the total number of turns. Small n is the number of turns per unit length. Do we understand this? Yes or no? I'll give you a minute to note it down. That takes us to the next concept, and the next concept is the concept of mutual induction. So what happens in self-inductance is that you have only one coil. You change the current in that coil. Magnetic field in the same coil changes. Flux in the same coil changes. And you have an induced EMF in the same coil. In mutual EMF, mutual induction, I have two coils. Bad. I have two coils. One coil is the primary coil, number one. One coil is the secondary coil, number two. Call them one or two as well. N1, N1, Phi1, and F1, as you can see here, are the values of the magnetic field, flux, and self-inductance of coil 1. The similar values are for coil 2. Now what we are going to do here is, I am going to pass current in the primary coil and I am going to change it with time. When the current in the primary coil changes with time, then magnetic flux in the secondary coil will also change with time. According to Lenz's law, this will induce an EMF, and this induced EMF will try to oppose the current in the primary. This phenomena is known as mutual inductance. So basically, current is changed in primary. This is the primary, and EMF is induced in the secondary. Do we understand this? And this induced EMF will oppose the change of current in the primary. This phenomena is known as mutual induction. Do we understand this? Can I have some raised hand that we understand this? I'll give you a minute to note it down. Okay, then let us move on ahead and see how do we calculate this mutual inductance. So what is going to happen is current is going to flow in the primary and flux will be linked in the secondary. The total flux in the secondary will be N2 into phi2, and N2 into phi2 will be equal to M into I1. M standing for mutual inductance. N2 and phi2 is the flux and number of turns of secondary. So my mutual induction or inductance becomes N2 into phi2 divided by I1, or N2 into B1 into A2 divided by I1. Why B1? Because magnetic field is created by the primary coil. Do we understand this? Yes or no? No or yes?
Yes, sir.
I'll give you a minute to note it down. Again, some important point. The units and dimensions of M and L, whether it is self-inductance or mutual inductance, are same. The mutual inductance again does not depend on current through the primary, and it is constant. Now, we have seen one formula, N2 into phi2 is M into I1. That is one formula of calculating the mutual inductance. Now, if the current in the primary changes with time, EMF will be induced in the secondary, and I will have the second formula, induced EMF in the secondary coil, remember, will be equal to minus M into dI1 by dt. So you can write it like this, E2 will be equal to minus M dI1 by dt. Do we understand the meaning of these terms, bacha? Please note it down, I'll give you time. Let's move ahead and note down the mutual inductance of certain configuration. Here I have two coaxial solenoids. We have seen the mutual inductance of a single solenoid that was mu naught n square A by L. Here the formula looks like this: mu naught n1 n2 A by L. N1 and N2 are the number of turns in the primary and the secondary. A is the cross-sectional area of the solenoid. Here we have assumed that the area is same for both, divided by the length of both the solenoids. Do we understand this? Please note this down. Done, sir. Then very well done, sir. Then we come to the next point where we have two concentric and coplanar coils. Remember, the formula looks a bit more complicated. The formula is like this: R1 is the radius of the outer coil. Remember this: R1 is the outer coil and R2 is the inner coil. Remember this: the formula is mu naught N1 N2 into pi R2 square. Remember, smaller coil का area divided by the radius of the bigger coil. Do we understand this? Please remember these things in the formula that I have marked, because you might make a mistake in the formula for R1 and R2.
Yes, sir.
Let's move ahead and see some golden points. If you have two circular coils, outer radius R1, inner radius R2, the mutual inductance is proportional to inner radius square divided by outer radius. For two square loops, it is similar to inner side square divided by the side of the outer square. Do we understand this? Please note this formula. Any of this formula is going to come, bacha, in your exam. Please note it. Then you might have a case where you have an outer square loop and an inner circular coil. Then the formula will look like this: inner coil ka radius square divided by the length of the outer square. Please note it down. Let's move ahead and see the next point where we can write the mutual inductance in terms of self-inductance, and this is the formula of writing mutual inductance in terms of self-inductance. M is equal to mutual inductance is equal to K times root over L1, L2. L1 and L2 are their coefficients of self-inductance. K is a constant which is known as the coupling factor. How do you get the value of this coupling factor? This value of coupling factor varies from 0 to 1. The entire flux of one coil is linked with the other coil. Coupling factor becomes 1. If it is not linked at all, the coupling factor becomes 0. The value of coupling factor is normally given to you, or a condition would be given. You can find out the value of coupling factor, and from there you can find out the value of mutual inductance. Do we understand this? Yes or no? No, yes.
Yes, sir.
Please note it down, beta. Well, as I said, the value of coupling factor K varies from 0 to 1. An ideal coupling where the entire flux is linked, the coupling factor is maximum, is equal to 1. Obviously, the coupling factor is not going to be 1. It's not going to be ideal. So it will vary between 0 to 1. The value of coupling factor comes from how they are linked to each other. In the next diagram, Pacha, we are going to see the different types of coupling, and then you will be able to understand how this value of K varies. So you can just note them down in your sheet. As you can see, in case number 1, it's an ideal coupling. So what you have done is you have one coil, and on top of that coil, you have put the other coil. So in that case, whatever flux is linked in the first coil the same flux will be linked in the second coil. So the coupling factor becomes 1. Do we understand this? If the two coils are separated by a small distance, we call that distance as air gap. Whatever flux is linked in coil 1 primary, the same flux will not come to coil 2, and therefore you will have the value of K varying from 0 to 1. Do we understand this? Yes or no?
Yes, sir.
You can see in case number 3 and 4, and very important cases. In case number 3 and 4, whatever I do in the primary, no flux will be linked in the secondary. In case number 4 also, whatever I do with the primary, no flux will be linked in the secondary. And in this case, the value of coupling factor will be 0. So coupling factor depends on how these coils are arranged. It depends on the orientation of the coil. At the same time, you can also define K as flux link with the secondary divided by flux link in the primary. Do we understand this, Bacha? One more formula for K. Do we understand this?
Yes, sir.
Great. I hope you are noting it down. Now, the last point for today's class is the points on which the magnetic, the mutual inductance depends on. These are the points. You have seen those points. It's important that you note them down. The mutual inductance depends on the number of turns, N1, N2. It depends on the self-inductances. We have seen the formula L1, L2. It depends on the area of cross-section. It depends on the medium. It depends on the distance. It depends on the orientation, how these coils are arranged, or it depends on the coupling factor. Do we understand this? Yes or no? No or yes?
Yes, sir.
I hope you have noted all these points down. Have you noted all these points down, bacha? All the points on which mutual inductance depend on. Have you noted it, beta? I'll give you a minute. Well, I hope you have noted down and you have the notes, you have the sheet. You can note down it in from your sheet. What we have done today is we have understood the concept of self-inductance, self-induction, and mutual induction. In self-induction, you have one coil, current in the coil changes, magnetic field changes, EMF is induced. This phenomena is self-induction. In mutual inductance, you have two coils. You change the current in primary, flux in the secondary changes, and you have an EMF induced in the secondary, which will try to oppose the current change in the primary. If the current is reducing, we will try to increase. In the next class, we will go on to the circuits of inductors. I'll see you there. I hope you have learned this class. If you have any doubts, I'm always there. Take care and have a nice day, beta everyone. Bye bye.